lecture, we're going to talk about the mole, which is the chemist's dozen. Before I describe what a mole is, I'm going to do some review of some concepts we learned early in the semester that are going to be necessary to work with the mole. First of all, this is an atomic symbol for carbon, and you can see that there's two numbers to the left, a superscript and a subscript. You may remember from the very beginning of the semester that the superscript is the mass number, which is the total number of protons plus neutrons in the nucleus. So remember, a proton and a neutron each have a mass of about 1 atomic mass unit. So if you have a total of 12 protons plus neutrons, you're going to have a mass number of 12. The bottom number is the atomic number, which is the number of protons in the nucleus. So you can subtract this and figure out that for this particular carbon isotope, 12 minus 6, that's got 6 protons, it also has 6 neutrons. So this is one isotope of carbon, but carbon has 3 different isotopes found in nature: carbon 12, carbon 13, and carbon 14. So carbon 12 has 6 neutrons, carbon 13 has 7, and carbon 14 has 8. All of these do exist, but carbon 12 is the most common. It's much more prevalent than the others. And because of this, and also because the mass of protons and neutrons, although it's very close to 1, it's not exactly 1. So basically, we figure out the average atomic mass, which is basically the average exact precise mass of all 3 isotopes. So for carbon, it's 12.011, so slightly over 12, again, because there is some carbon 13 and 14 isotopes present. I'm now going to review what formula mass is. So this is something that we talked about in the for the last exam early on. The formula mass of a molecule is the sum of the mass of all its atoms. So if we have chlorine, the atomic mass is 35.453. So that's the mass of all the isotopes of chlorine present, and that's the exact number for, or basically the atomic mass of chlorine. Now remember that in nature, chlorine, it's a diatomic molecule. That means it exists as Cl2. So the formula mass is basically going to be 2 times 35.453, or 70.906 atomic mass units. So the formula mass you get, what it means is it's the mass of all of the atoms in a compound. So we can also do a slightly more complicated compound, H2SO4. And to figure this out, we have the mass of hydrogen. And for the above one, I did the very exact mass. I'm just going to do a more rough estimate. So for hydrogen, we have it has atomic mass of 1. And there's 2 of them, so that's 1 times 2 is 2 atomic mass units. For sulfur, it's got atomic mass of 32, and again, you can look this up in the periodic table. And there's 1 of them, so that's 32. And for oxygen, it's got an atomic mass of 16, and there's 4 of them in the H2SO4, so that's 64. So to get the formula mass, we add all of those together, and the formula mass of H2SO4 is 98. And so let's do this for another compound that's got aluminum. Okay, now let's determine the formula mass of Al2SO4 3. So this has got a sulfate ion. The SO4 is sulfate, but it's got aluminum instead of hydrogen. And because of to make sure that we have a charge neutral compound, the ratio is a little bit different. So if we look at this, aluminum from the periodic table has an atomic mass of 27, and there's 2 of them, so that's 54 atomic mass units. Sulfur is again 32, and this time there's 3 of them, so that's 96. And oxygen, there's 16, it's got an atomic mass again of 16, and then so it's there's 4 of them, but then there's 3 sulfite um, uh, anions. So basically, that's 4 times 3 is 12, so that's 192. So that's just in this, I'm trying to emphasize that you need to, if you're figuring out the formula mass of something that's got something in parentheses and a polyatomic ion in parentheses, you need to multiply out to figure out the total number of atoms in that to figure out the formula mass. So basically, if we add these numbers together, the formula mass of aluminum sulfate is 342 atomic mass units. Now compare that to H2SO4, it's heavier, it has more mass, and basically the reason for that is we've got more sulfate polyatomic ions. We got 3 as opposed to 1, so that's going to be 3 times as much. And aluminum is heavier than hydrogen, so that's why it has a higher atomic mass. All right, now that we've done that review, we're ready to describe what a mole is. So a mole is basically, as I said in the very first slide, like a chemist's dozen. So think of a dozen eggs. So a dozen means 12. So a dozen is commonly used to for eggs and bagels. If you have, and it means the same thing no matter what you're talking about. So you can have a dozen eggs, you can have a dozen bagels. Either way, you have exactly 12. A ream is another word that has a similar meaning. So basically, it's a word that specifies a particular amount. So one ream of paper is 500 sheets of paper. It's usually used for paper, but you could use ream to indicate an amount of anything, and it's always going to be 500 of whatever that is. So basically, a dozen, a ream, and a mole are all units used to indicate the number of objects. We could use a dozen to indicate atoms. We could say we have a dozen atoms, and that would mean we had 12 atoms. But if we look at a mole is actually it's 6.022 times 10 to the 23rd. So that is what a mole, when we see a mole, when we say we have a mole of something, that means that that's how many of that item there are. So if we have 1 mole of S in the upper right here, so that's sulfur, the yellowish substance is sulfur. So 1 mole, that's about 1 mole of sulfur, and in that sample, there's going to be 6.022 times 10 to the 23rd atoms. Now, obviously, it's not going to be an exact measurement. We probably have a small number more or less, but that's approximately how many sulfur atoms are present in that. And on the right, the black substance is carbon, and that shows approximately 1 mole of carbon, which again is 6.022 times 10 to the 23rd atoms. So if you look at the mass, this shows the mass. 1 mole of sulfur is 32.07 grams, and 1 mass of carbon is 12.01 grams. So why does it weigh less? Well, that's because the carbon atom is lighter. So basically, if you have exactly the same number of carbon atoms, sulfur is heavier, so there's basically going to be more mass if you've got the same amount of atoms. So why do we use the mole, or why do we use any of these numbers? Because they're practical. So like when we buy a carton of eggs, somebody decided a while ago that a dozen was a good amount of eggs to sell. So it's just easy to say a dozen eggs. It's easier. It's an easy way to explain it. And the same with like a ream of paper. We know that there's exactly 500 sheets of paper. Mole is a very convenient number for atoms. So remember, atoms are really, really tiny. So if we used a smaller number, if we said a dozen atoms, that would be so few that you couldn't see them, you couldn't work with them. Whereas if we have a mole of atoms, you can see there's like a mole of sulfur here, a mole of carbon. That's an amount that you could put in a beaker and use to make a compound or manipulate in some way. So this is kind of a convenient amount. And y is at 6.022 to the 10 to the 23rd, which is kind of a bizarre number. We'll get to that in a minute. Okay, and I want to emphasize here that when we're talking about an amount like a dozen or a ream or a mole, size doesn't matter. So if you have a dozen eggs, you could use a dozen to describe 12 quail eggs, which are 10 grams, 12 chicken eggs, or 50 grams, which are 50 grams, or 12 ostrich eggs, which are 1,500 grams. So if you have 12 ostrich eggs, you could make a lot of omelets with that because that's a very large amount of stuff in the egg, but it's the same number, like it's always going to be 12, whichever one you're talking about. So basically, a dozen is a dozen. And the same is true for a mole. If you have a mole, you have 6.022 times 10 to the 23rd, and as I mentioned in the previous slide. So if you're talking about a mole of atoms, some atoms are bigger than others, so that one mole is going to actually have more mass, even though there's the same number of atoms. And we can also use moles to measure. Now, a mole, like a dozen, is used to indicate a number of particles, and it's usually used to measure very tiny particles because it's a very large number. You wouldn't measure a mole of eggs because that would be more eggs than you could possibly get. But it's a very useful number for measuring the number of atoms, molecules, or formula units, and it's always going to be the same. So if we have 1 mole of oxygen atoms, that's 6.02 times 10 to the 23rd atoms. And here I rounded. It's not an exact, it's 6.022, and then you can even add more significant figures, but we'll just say 6.02 times 10 to the 23rd atoms here. Now, if we have 1 mole of we can use, so that's atoms. We can also use a mole to describe the number of molecules. So if we have 1 mole of oxygen molecules, that's 6.02 times 10 to the 23rd molecules. We could have 1 mole of hemoglobin, which is a protein that carries oxygen in the blood. And this is the chemical formula for hemoglobin. It's huge. It's got 2,952 carbon atoms and then a bunch of other kinds of atoms as well. But if we have 1 mole, we have 6.02 times 10 to the 23rd molecules. So obviously, if we have 1 mole of hemoglobin, we're going to have a lot more mass there than if we have 1 mole of oxygen. But if we count the number of particles, it's going to be exactly the same. And then if we have 1 mole of NaCl, that's 6.02 times 10 to the 23rd formula units. So if you remember from some previous lectures when we were talking about ionic compounds, NaCl, or sodium chloride, a formula unit has 1 sodium atom and 1 chlorine atom. And then we can have a formula, it basically can be a crystal could have many, it's going to have the same ratio, but it could have many sodium and chlorine atoms. So a formula unit is 1 of each. And if we have 1 sodium and 1 chlorine, that's 1 formula unit. And if we have a mole of those, it's 6.02 times 10 to the 23rd formula units.